Welcome to Calculus. Today we will investigate determining concavity of functions. We'll take a look at two examples. Our first example is this polynomial cubic function f of x equals 2x cubed minus 6x plus 6x minus 3. And we really have three tasks. I want to start off by finding any local extrema of f. Then I want to determine the intervals on which f is concave up and on which it is concave down, and then to use that information to determine, are there any points of inflection? Well, let's begin with that first task, finding the local extrema of f. So recall, to find a local extrema, we're looking for a point on the graph where the tangent line would have a slope of 0. So the go-to strategy there is take the derivative of the function, set it equal to 0, and solve. So let's do that first. I'll find the derivative of this function, f of x, is going to be 6x squared minus 12x plus 6. And then again, I'm interested in the places on the function where the slope of the tangent line is equal to 0. That would indicate that I've either got a maximum or a minimum. So I'm going to set 6x squared minus 12x plus 6 equal to 0 and solve. So I see I've got coefficients of all divisible by 6. So we'll divide that out, and that'll give us this simplified quadratic x squared minus 2x plus 1 equals 0. And that I can solve by factoring. X squared minus 2x plus 1 is equivalent to x minus 1 times itself. And that's going to give us one solution. I can set up both small equations, but they're identical. So the solution to this quadratic is going to be x equals 1. So it looks like I've got a local extreme at 1, or some type of critical point. So at that point, what I want to do is decide what is happening to the sign of the derivative on either side of 1. So we'll just create a real quick table. This will help us determine if that's a maximum, a minimum, or neither. So on our table, I really just want to find what's happening around 1. So I'll put 0, 1, and 2. And f of x, we're going to go for the original. Actually, we're going to go for the derivative, because I'm interested in what's the sign of the derivative. So again, I'm taking this quadratic and I'm going to plug in 0. So that's going to be 6 times 0 squared minus 12 times 0 plus 6, and that's going to yield 6. One we'd already calculated, that's 0. 6 times 1 squared minus 12 times 1 plus 6. That's 6 minus 12 plus 6, and that is in fact 0. And then we want to find the sign here at 2. So 6 times 2 squared minus 12 times 2. So that's going to be 24 minus 24. So the first two terms cancel, plus 6. So this is also going to be 6. So we don't see any change of sign on either side of the critical point. And so it's neither, and let's go ahead and put this point 1, comma, let's find its value in the original function. So 2 times 1 cubed minus 6 times 1 squared plus 6 times 1 minus 3. So that's going to basically be 2 minus 6 plus 6 minus 3. That should be negative 1. Is neither a max nor a min. So there's no local extrema on the graph. And one thing we can do just to convince ourselves that that's in fact the case is take that original function and just look at it on a graphing calculator. So I'm just going to record the original function 2x cubed minus 6x squared plus 6x minus 3. And we just want to take a look to see what's happening on the graph to corroborate our algebra work here. So I'm going to type in that function, again, 2x cubed minus 6x squared plus 6x minus 3. So I see that point there, 1, -1, is a critical point, but it's not a minimum or a maximum, because there is no minimum or maximum on this function. So it is good to just kind of check as you go with a graphical follow-up on the algebra. Okay, so we've determined part A, there are no local extrema. Part B says determine the intervals on which f is concave up and on which it is concave down. So we need to determine what's concavity mean, and then how do we determine if it's concave up or concave down. So the way that we would define concave up is it's a function. We would say that it's concave up if, and we'll specify concave up on the interval a to b if the graph of f lies entirely above all of its tangent lines. So just to give an example about what that might look like, a concave up function would look something like that blue curve. And what we're claiming there is that that curve's entirely above any tangent line. And you can guess how we would define concave down. We would say a function f is concave down on the interval from a to b if its graph lies below all of its tangent lines, if it lies below its tangent lines. So again, just to give an example of a sketch of a graph that's concave down, it would look something like this curve, where the entire graph lies below any tangent line. Now, that's how we define concavity. To find where a function is concave up or concave down, we really want to look at the second derivative and then compare the signs. So again, what we'll do is we'll take the second derivative, set it equal to 0, and solve as we did for the first instance. So let's do that right away. I'm going to take the second derivative. So if my first derivative is 6x squared minus 12x plus 6, my second derivative is going to be 12x minus 12. And again, I want to set that equal to 0 and solve, similar to how we did on our first derivative. So I'm going to add 12 over here. And that'll give us 12x equals 12. Very simple solution at that point. Divide by 12 on both sides, and we get the x value again of 1. So really what this is corresponding to is the same point that we found 1, -1 on the original function. What we need to decide is now what's happening in terms of concavity. So we'll do a similar table to what we saw with the first derivative, but we're going to now calculate using the second derivative. And again, we're interested in, is there a change of sign to the left of that critical point at 1, or is there no change of sign? So now I'm going to plug in 0. So 12 times 0 minus 12. So that's negative 12. 1 we plug in and we know we get 0 because we just solved for that. And then 2, 12 times 2 minus 12, that's 24 minus 12 is 12. So we do see a change of sign for the second derivative. And what we can at that point conclude is that I have essentially an inflection point. Whenever I have concavity that changes sign from negative to positive or positive to negative, I can see that I've got a change in concavity. So if it's a positive value, what we would say is that the function for those values of the domain is concave up. So just taking my table here from negative infinity to 1, the sign is positive, and so this would be concave up. I'm saying that wrong because I'm not minding my signs here. So the sign actually is negative. It was negative 12 when we did the output, so it's actually negative concave down. And then from 1 to positive infinity, this is where the sign of the second derivative has positive output. And so that's concave up. And whenever I see a change from concavity, either from positive to negative, concave down to concave up, or vice versa, concave up to concave down, what that says to me is that this point, 1, negative 1, is not a max or a min. It is an inflection point. And an inflection point is exactly that. It's where my concavity changes from either concave down to concave up or concave up to concave down. And again, that look at the function would support that. If we just look back at the graph that we had plotted earlier, that point 1, 1, I'm sorry, 1, negative 1, definitely to the left, that's concave down. All the tangent lines would lie above the graph. And then past 1 to the right, the graph is concave up. All the tangent lines would be below the actual curve. All right, so that concludes that first example of a polynomial function. We found that it had no extrema, but it did have a change in concavity, so it had a point of inflection. Let's take a look at a second example. So this is a rational polynomial, rational exponent polynomial. F of x equals x to the power of 2/3 times x squared minus 8. And our task is the same. I want to find the local extrema. I want to determine the intervals on which f is concave up and on which it is concave down. And then determine, are there any points of inflection? So again, we'll start with that local extrema task. And what I'd like to do to this function before I start taking the first derivative is I want to distribute x to the power of 2/3 to the x squared and the x and the minus 8. So I'm multiplying here. So x to the 2/3 times x squared is going to be equivalent to x to the 2/3 times x to the 6/3. Now the reason I write it that way is we got to add those exponents. So that's going to be x to the power of 8 over 3 minus 8x to the power of 2 over 3. And that's the function I want to work with. That's going to be easier to take derivative. So we'll do that right away. So I'm going to take derivative of the function. So that's going to be 8/3 x to the power, if I subtract 1 from 8/3, that's 5/3, minus 2/3 times 8 is going to be 16 over 3. X to the power 2/3 minus 1 would be negative 1 over 3. And I want to rewrite that in this way. 8/3 x to the 5/3 minus 16/3 times 1 over x to the power of 1/3. Now I write it that way to help with the solution when I set it equal to 0. So I want to do that right away because I'm interested in, again, are there any critical points, which would lead me to discovery of local extrema, local max or local min. So I want to solve this. So the first thing I want to do is I just want to get rid of these coefficients if I can. So I'm going to divide by a thirds, since I see that both of these terms on the left are divisible by 8/3. And then we'll bump our solution over to the left just to conserve space. So then we've got x to the power of 5/3. 16/3 divided by 8/3 is 2. So that's going to be 2, and I can just put that over x to the power of 1/3. So then I've got two things I need to do. First of all, I need to say that there is a restriction. I have x to the power of 1/3 in the denominator. That can never equal 0. So I am interested in both solutions and also any discontinuities. So that's going to be a discontinuity at 0. So I'm just going to note that that's an x value we need to keep an eye on. I don't know if it's a max, a min, or neither. I just need to watch it. So I got x equals 0, but then I need to solve this as well. So I see that if I could multiply by x to the power of positive 1/3, I could cancel this denominator. So I'm going to multiply each term in the equation by x to the power of 1/3. So what that's going to do here on the left is turn this into simply x to the power of 6/3, which is power of 2, minus 2 equals 0. So it much simplifies here. Note it was important for us to find this x equals 0 undefined place first before I cancel that denominator. But now I'm good. So I'm going to add 2 to both sides, and I get x squared equals 2. And then to finalize that solution, I take square root, and I get this really double value, x equals plus or minus square root of 2. So these are the important points for us to consider as critical numbers. 0, and then negative square root of 2, positive square root of 2. So what we want to do at this point is decide, are they local minima, maxima, or neither? So I'm going to create a table like we did in our previous example, and I just want to look and see what's happening around these values. So I'm going to place negative 2, negative square root of 2. That's the value of about negative 1.414. We'll look at negative 1, 0, 1, square root of 2, and 2. So just to facilitate ease of calculation here, I want to go to the calculator to get that output. So I'm just going to record the derivatives function, which was 8/3 times x to the power of 5/3 minus 16/3 times x to the power of negative 1/3. And let's get some table values. So I'll input that new function. This is the value, the derivative function. So it's 8/3 x to the power of 5/3 minus 16/3 times x to the power of negative 1/3. And that's given me this kind of double cubic function. If I zoom out, I can kind of see that it is a function. It's really a rational function with a very steep slant asymptote. So what I'm interested in is really the signs here. So let's create our table. And we've already set out which values we need. So at -2, I need negative square root of 2. And notice the calculator is giving us an approximation. That's basically 0 for both of those. So I just want to record this. So the output at -2 is about -4.23. Negative square root of 2 has the output of 0. -1 output of 2.67. 0 is undefined. And we saw that already. 1 is -2.67. Square root of 2 is 0. And then 2 has the value of 4.23. So I just wanted to get really the signs on those outputs, and that'll help us determine what sort of extreme it is. Is it a maximum? Is it a minimum? Is it neither? So here's x, the derivative. So if our value at -2 is -4.23, and that changes at -1 to 2.67, that means I have a change from negative to positive. So when I think, okay, if the graph is decreasing to the left and then increasing to the right, this has to be a minimum value. All right, 0 is undefined. And then 1 has the value of -2.67. So that's negative. So I can make a claim here. 0 is undefined. It is, in fact, undefined, but it is also at a change between a positive and a negative. So this, my feeling is it's some kind of maximum value. The function's increasing and then it's decreasing on either side of 0. Square root of 2 is 0. And then 2 has the value of 4.23. So again, I've got another change here from decreasing to increasing. That's another minimum. So let's list out what we've got so far. -2, I'm sorry, let me make sure. Negative square root of 2, comma, and then I need to grab that point from the original function. 0 something, and square root of 2, comma, something. So I need to come up with those values. So what I would like to do is, again, is go back to the original. Well, actually, let's just calculate it right here. We just have 3 values, and we can just plug it into the original function. So I'll just make a real brief table here. So this is going to be not the derivative, but the original function. I just want to get the y values here for these points. So if I plug in negative square root of 2, so that's going to be negative square root of 2 to the power of 2/3 times negative square root of 2 squared minus 8. So that's going to have the value negative square root of 2 to the power of 2/3. The numerator will square it, so it's just going to become positive 2. So it's really the cube root of 2 from the denominator. That becomes my root. And then from the parentheses, again, negative square root of 2 squared is just 2 minus 8 is -6. So I could put the output is -6 times the cube root of 2. If I put in 0, let's see what happens with 0. So that's going to be 0 to the power of 2/3 times 0 squared minus 8. Well, that doesn't really matter much. 0 times anything is going to be 0. So actually, that's the origin. And then if I plug in square root of 2, I think we'll get something similar to what we saw in the beginning. In fact, the same value. Because on the first one, the negative was canceled by these squares. So again, square root of 2 squared from the numerator is going to be 2. the denominator is a root, so cube root of 2. And then similarly, in the parentheses, square root of 2 squared 2 minus 8 is negative 6. Negative 6 times the cube root of 2. And let's just identify what these are. So again, this first point's a minimum, second one's a maximum, and the third one's a minimum. Let's confirm what we've done algebraically here just by looking at the original. We've looked at the derivative graph. We still haven't looked at what the original graph looks like. So let's just take a moment to check our algebraic work here. So there's the derivative, and we're kind of familiar with that by now. Here's the original. So we'll call it g of x just to help old Desmos. So x to the power 2/3 times in parentheses x squared minus 8. And so this is that red curve. And so what we're seeing here is this point, negative square root of 2. If I type in cube root of 2, I forgot the negative 6. That has the value of about negative 7.5556 if I round. So that checks out. That's my minimum on the left. Here, 0, 0, that's our cusp there in the middle of the graph. So that's why it's shown up undefined on the derivative. Can't really take the derivative at that point. But it is a maximum on the graph. And then here on the right, square root of 2, negative 6, cube root of 2. All right, so we've completed the first two tasks. And that look at the graph does corroborate what we're seeing with the algebra. What's left for us to do is determine the intervals on which f is concave up and on which it's concave down. So remember, that's the second derivative. So I do want to just take a moment to identify this is my first derivative, just to kind of catch out of all the writing here. So what we want to do now is take the second derivative. And this is the test for concavity. So my second derivative is going to be 8 over 3 times 5 over 3. So that's 40 over 3. X to the power of 5/3 minus 3/3 is going to be 2/3. And then negative 16 over 3 times negative 1 over 3 is plus 16 over 9. And I've made a mistake here already. That first denominator should also be 9. And then for my x here, the power is negative 1/3 minus 3 over 3, so negative 4/3. And that equals 0. So again, I do set it equal to 0, and I want to solve it similarly to how we solved the first derivative when setting it equal to 0. So I'll take a look at the coefficients to begin. Looks like I can divide by probably 8 over 9. 8 is divisible by 4 into 40 and into 16. And we'll divide that on each term. So what that'll give us for our next step is 5x to the power of 2/3 plus 2 over x to the power of 4/3 equals 0. So a similar setup here. I can cancel this power x to the power of 4/3 by multiplying each time by that same term. So I do see a cancellation there in my middle term. First term becomes 5x to the power of 6/3, which is squared, plus 2 equals 0. So as I try to solve this one, I can subtract 2 over. It's really got a similar setup to what we saw with our first derivative equation set equal to 0, but there's a major difference here. Notice as I moved that 2, I had to subtract it. So I'm keeping on with the algebraic steps here, but I'm running into a problem. I get x squared equals negative 2 over 5. If I try to take the derivative, I'm sorry, if I take the square root, I've got the derivative on the mind of a negative number, all of a sudden I'm not in real numbers anymore. I have jumped over into imaginary numbers. And so what I'm seeing is that there is no real solution for the equation of the second derivative set equal to 0. And what that's saying to me is that there aren't any changes in the concavity. So what I'd like to do is just take a look at that second derivative and then just compare it with the original graph to see why are we getting this result where I can't come up with a solution for this derivative having a slope of 0 at any point. So I'm just going to write the function that we wrote down here for second derivative. And then let's again just look at the graph to help with our analysis. So we'll call this one h of x. So it's 40 over 9, x to the power of 2/3 plus 16 over 9 times x to the power of negative 4 over 3. And so notice that is going to give us a rational function that never gets near the x-axis. And so we can see graphically why our attempt to solve this equation by setting it equal to 0 did not work. Remember, it gave imaginary solutions. So if I just look at this graph of the second derivative, it never goes below the x-axis. So again, what that says to me is the sign is always positive, which means that this graph is always going to be, you've got it, concave up. And if I include the graph of the original function, it really does present itself that way. This graph is always concave up. Every tangent line that I would draw on this graph, whether on that left side or the right side, would be below the function. So our algebraic work, although it seemed like it didn't give a lot of information, we weren't able to solve that equation, is that there is no change in concavity, which means there's no points of inflection. And again, where we saw that no change in concavity is when we were unable to solve the second derivative when we set it equal to 0. And again, if I don't have any change in concavity, I won't have any points of inflection. Thank you for joining for this investigation of determining concavity of functions. See you soon.